Hello everyone, I'm gonna present our project for the subject SCA and industrial controllers. So for this project we use the theory of discrete event systems, automata and supervisory control. This theory allows control a discrete event system in order to satisfy a given set of logical performance objectives. Using Supremica, an open source software that allows modeling these automatas and do composition operation of those automatas, we can start from some models of automata that represent the behavior of some subsystem of our plant. After that, we can do an operation called parallel composition. All these operations are operations that use all the mathematical theory behind discrete event system. So we can build a total model of the plant and we can find a supervisor that contains all the behavior of our plant. So we can simulate this plant in Supremica and we can see how the states are changing and which event is available in every condition. With the supervisor, we can generate a XML file. We can translate this file using a Python translator that was developed for one of us. After that, we will have unstructured text. This structured text is um, designed for Studio 5000, so we can use Studio 5000 to control a plant. In this case, uh, we connect factory I/O to our pack in the laboratory, so we can see how our digital twin is working.
First of all, I'm going to introduce you to Supervisory Control Theory, which we model every actuator and every signal as an state or an event, respectively. As we can see, we have a little more here where we have a state of conveyor off and conveyor on. This automata corresponds to the first conveyor of our plant. It changed from a state to a state in function of events. As you can see, here we can see one event and another event. The first is GD out to and on, and the other GD out to off. It means that the signal in this point goes on and here goes off. That is an event. We can model every actuator of our plant in the same way. You can see here the clamp of the first conveyor, the or X axis, or another conveyor, or another clamp, even or knife. As we can see, we are already telling which actuator are getting on and going off. Those are controllable events. It means that we can control when they goes on and when they goes off. It's different when we have something like a signal from our sensors. Here we can see the event GD in or on, which represents our sensor here, lit up place, GD in or on. it is a sensor in our plant that says here, that says that our clamp is clamped. Is related with this signal. We can see it right here. Right? Same as this, we have relationated every signal in the input and every actuator at the outs of our PLC. After we model every one of our actuators, then we have to model the requirements. The requirements are meant to define and control the full functioning of our plant. So I'm going to explain you the lead conveyor, the first conveyor that we have. We start here our first state. Then when we get the GD in 15, which GD in 15, which corresponds with our on button, it changes to S1. When we go here, our control will turn on this signal GD out to on. As we can see in our model, GD in 15 is our start button and our GD out 2 is our actuator of the conveyor. Then it stays on until they feel the falling edge of the sensor lit up place in the input GD in 2. As we can see right here. When it feels that, it changes to the state S3, and then it sends the controllable signal GD out to off and goes back to state S0. Then it will wait until all signal GD out 6 is on, and we turn on GD out 7. 6 correspond to our C axis, and or 7 correspond to the grab. So it will turn off until we extend or activate the movement, the zeta movement, and we turn off the grab. This corresponds to the moment when we complete the production of a piece. Please be aware that all the signals that are not controllable, those three, are modeled like simple events, but our controller does not have any control of when, of where it happens. Even though we have to make all this auto reference to all the states to say to the controller that no matter what, which uncontrollable event happened, if we are not expecting it, it will stay in the same state. After we model every behavior of every requirement of our plant, as you can see, those are little graphs, really lots. And as I have explained you, those are pretty much simple and natural than a ladder implementation. We can combine all of these automatas and make just one, right? In this case, for simplicity, and trying to reduce the number of lines at the end of this program, we combine into automatas, dividing our plant into parts. The first of all includes the base conveyor, the base clamp, and the knife. The second one has the clamp lead, the lead conveyor, and both axes. As you can see, then you have a really big automata, but for the implementation from the basic of the theory, we are sure that these automatas will satisfy the behavior requirement. After we have those automatas, yeah, we got them through combining here any number of items. As you can see, we have created a new one, but we are not going to use it. We go here to the simulator, and you can see how all of those work. Even if you don't see them in your screen, those automatas will be supervising the fulfillment of every requirement you have set up. So, for example, we come here, we go play, and we can put any event. It won't happen anything until you choose to get the start signal. Once you get the start signal, see, things start to happen. Then we have two controllable signals, and those are start base conveyor and start lead conveyor. So we're going to start the lead conveyor. As we can see, it's already on. We want to start the second conveyor. It's already on. Then we will wait until the next signal. In this case, will be lead at place, for example, and base at place. After the controllers receive the signals, we can either take off the conveyor, one of the conveyor two. So we want to put both off, and well, you're gonna see it in the simulation. You can see here you can simulate the behavior of your plan and all the actuators you have. After you have your supervisor working nicely, you come to the analyzer, you export it as XML, save it, and we go to PyCharm. Here we have developed a little translator, changing from our events and asynchronous from our asynchronous events and states to a later code. So, ignoring all the code we just have to put here the name, for example. In this case, we have banda 1 and banda 2 representing both automatas that we generate. And then right, you can see in our console is rated or ST code, and we generate a different file with the same code. Yep.
Now we can copy our code and paste it in our Studio 5000. Then we can see here how we have our two automatas, the first one and the second one. This code works for every state and every signals and every combination that we have made in our specification and our supervisor from Supremica. Also, you can model an signal that you need have a protocol. You can do it here, and it's okay. Now we can verify your connection to the PLC by the ping. We can see that we have the connection right established. Then we can upload our code to the PLC from Rockwell, and we can verify in our factory that everything is working as must be. We have downloaded our code at the PLC, and here we can see. By the way, you have to create it all your tags because Studio 5000 doesn't allow to create the tags in the code est. To avoid the error if you have a tag that doesn't exist, you can click with the right button from your mouse in your tag and create the tag in the code. We have created another tag, so we have to download it again to the PLC. We are doing.
For example, this one, it will find you an error. So you just right click here and new tag. And that's all. That happened for everybody else. So go online again. Okay, for that little change, I'll have to do it again. There's no problem. Just wait a minute.
Now we can start our plant in the factory IO. Then we push our start button and our plant is start working or simulation. Now you can see how the tags are changing in our Studio 5000. That's those tags from our code, and that shows you that our automata are working properly. That's all.
We also use another software, is Open PLC. Is similar to Studio 5000. The difference between both software is that in this interface we have less options than Studio 5000. This software is not for connect a real PLC because we can't use this kind of software for PLC with specific brands. So we can do here simulate PLC for see how is the behavior of our plant after simulating. So we can see here, for example, here in Studio 5000, we can see this kind of data type is a specific function block called FDB one shot. This kind of data type is used for falling edge when a sensor change his value, so we can activate, for example, a conveyor when the falling edge is detected. So this kind of data type is very useful for programming in structured text. So here in OpenPLC we can see we don't have this kind of data type. We have this F3 data type, and like the syntaxes of the programming code is a little bit different. We can see here, for example, this is the way for capture, for example, the input bit. In Studio 5000 we have, for example, here we have an input bit and an output bit here, and when we are programming here in our main ST, the way you have to use the this kind of data type is like that for the input bit and like that for the output bit. And in OpenPLC, this is the way to use the input bit, and for manipulate or use the output bit, you have to do this kind of syntaxes, this kind of notation. So after generate our code, you can run and track all the variables with this tool, but we can also generate a program for OpenPLC runtime. We can do that. After that, we need to run our OpenPLC runtime. This software will run in our local host. We can start OpenPLC runtime. So we have to wait a little bit. And you can see here that our OpenPLC runtime is running right now in this port, so we can go there. Okay, this is the interface of the OpenPLC web server. You need to use some credentials for use this software. You just have to put in username OpenPLC and password is the same OpenPLC. So okay, so for blood our EST code, you need to go to programs. So you need to select the file. So here, this is the file that OpenPLC editor generate before for us. Is this one. So you need to do a little configuration for the communication between OpenPLC runtime and factory I/O. So here you need to go to file. You need to see the drivers, and this is like the structure of our output and input variables in with this kind of communication. So you have to select Modbus TCP because this is the protocol that we need to use for communicate bot softwares. And you can see here our IP. So here in slave devices, you have to put the same IP address and select all the holding registers, outputs, inputs. These outputs and inputs was created before here in OpenPLC editor. You need to select the location of our input or our output, for example, here. And this is the notation for every input. Okay, so here you select how many inputs and outputs do you need, and you have to select the port and the ID of the slave. And here you put the same configuration. After that, you save the device and you can start the PLC. So right now is running in this port open PLC runtime. So we can start. We can go to factory IO. So after checking all our information, our configuration, you can press the button start. You need to start the simulation first. After that, you can use this button. And right now, you can see all the simulation is working correct in a good way, correctly. So you can use OpenPLC like using Studio 5000 for simulate a digital twin without a PLC, a physical PLC. And this software is an open source software, and you can use also hardware, not like a PLC, but you can simulate a PLC with an embedded system like Raspberry Pi or Arduino. So it's really useful for simulate some things and do a digital twin on a physical plant without expensive software.